Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Henri Becquerel's investigation into penetrating radiations from a phosphorescent substance, published in 1896, occupies a pivotal position in the annals of physics. It marked the genesis of radioactivity, an entirely novel phenomenon that fundamentally altered prevailing understandings of matter and energy. To fully appreciate its significance, one must first examine the intellectual milieu that fostered its inception. The late 19th century witnessed an explosion of discoveries related to electromagnetism and atomic structure. Wilhelm Conrad Röntgen's recent announcement of X-rays generated intense scientific curiosity. The ability of these newly discovered rays to penetrate opaque materials captured the imagination of researchers worldwide, including Henri Poincaré, whose musings on fluorescence and X-ray generation sparked Becquerel's investigation. Poincaré conjectured a possible connection between the phosphorescence of certain materials and the emission of X-rays. This suggestion was rooted in the observation that the Crookes tube used to produce X-rays also exhibited phosphorescence. He proposed the potential for phosphorescent substances to, when excited by ordinary light, emit penetrating rays similar to Röntgen's discovery. Becquerel, a scion of a family deeply entrenched in the scientific establishment of France, possessed a unique advantage. His father, Alexander Edmund Becquerel, made significant contributions to the study of phosphorescence and solar radiation. Henri's inherited a substantial collection of phosphorescent materials, including uranium salts, which proved instrumental in his experiments. More importantly, he inherited a tradition of meticulous experimentation and a keen eye for detail. Becquerel's initial experiment involved exposing crystals of potassium uranyl sulfate to sunlight. Following Poincaré's suggestion, he expected these phosphorescent crystals, upon excitation, to emit penetrating radiations capable of affecting a photographic plate wrapped in black paper. The results of his early trials were indeed affirmative. The photographic plates exhibited darkening, seemingly confirming that the uranium salts, after exposure to sunlight, emitted penetrating rays analogous to X. However, a serendipitous event in late February 1896 altered the trajectory of Becquerel's research. Inclement weather prevented him from exposing the uranium salts to sunlight for several days. Impatient to continue his investigations, he decided to develop the photographic plate that had been stored alongside the unexposed uranium crystals. To his astonishment, the plates exhibited a strong darkening, despite the absence of any prior exposure to sunlight. This unexpected finding led Becquerel to realize that the uranium salts were emitting penetrating radiation spontaneously, without the need for external excitation. Becquerel then embarked upon a series of meticulous experiments to characterize radiations emitted by uranium. He meticulously documented the effects of these radiations on different materials, including photographic plates and various gases. He demonstrated that the radiations could discharge an electroscope, indicating their ability to ionize air. He also observed that the intensity of radiations was independent of the chemical form of the uranium. Compound emission depended solely on the presence of uranium itself. Crucially, Becquerel ruled out phosphorescence as the source of these radiations. Phosphorescence, by definition, involves the emission of light following exposure to a source of excitation. Becquerel's experiments demonstrated that uranium emitted radiations continuously, even when stored in complete darkness. This ruled out possibility that the observed effect was merely a delayed form of phosphorescence. He also ascertained that the intensity of radiation was unaffected by changes in temperature or pressure, further supporting the spontaneous nature of the phenomenon. In essence, Becquerel's 1896 paper details the discovery of a new form of radiation, qualitatively different from both light and X-rays. He demonstrated that uranium emitted penetrating radiation spontaneously, without any external source of excitation. These radiations possessed the ability to affect photographic plates, ionize gases, and penetrate opaque materials. While Becquerel did not fully understand the underlying mechanism responsible for this radiation, he meticulously documented its properties and laid the foundation for future investigations. His meticulousness in describing the experimental setup, observations, and deduction contributed to the work's lasting impact. The immediate impact of Becquerel's discovery was significant. It spurred intense interest among physicists and chemists, prompting them to investigate other elements and compounds with similar properties. His findings directly influenced Marie Curie, who, along with her husband Pierre Curie, embarked on a systematic search for other radioactive elements. Inspired by Becquerel's work, The Curries investigated various minerals and discovered that thorium also exhibited radioactive properties. Their subsequent isolation of polonium and radium further cemented the importance of Becquerel's initial discovery. Marie Curie later explicitly acknowledged Becquerel's pioneering work as a crucial stepping stone to her own research. The conceptual framework provided by Becquerel's observations directly impacted scientific understanding of atomic structure and matter. The spontaneous emission of radiation challenged long-held assumptions concerning the immutability of atoms. Prior to Becquerel's discovery, atoms were considered fundamental, indivisible units of matter. Radioactivity, with its inherent instability and transmutation implications, shook convictions. Ernest Rutherford, building upon Becquerel's and the Curries' work, used alpha particles emitted by radioactive substances as probes to investigate the structure of the atom. His gold foil experiment, performed in 1909, revealed the existence of a small, dense, positively charged nucleus at the center of the atom, surrounded by orbiting electrons. Rutherford's model of the atom, which superseded earlier plum pudding models, a direct consequence of radioactive phenomena. Furthermore, Becquerel's discovery had profound implications for energy conservation principles. The spontaneous emission of radiation appeared to violate the law of energy conservation, as it implied that energy was being created ex nihilo. It took subsequent investigations, particularly Einstein's mass energy equivalence principle E=mc², written as energy equals mass times the speed of light squared, to resolve this apparent paradox. Radioactivity provided direct experimental evidence for the interconvertibility of mass and energy, confirming Einstein's theoretical predictions. Becquerel's work also had immediate, tangible applications in medicine and industry. Early researchers quickly recognized the potential of radioactive substances for treating cancer. Radium, in particular, was found to be effective in shrinking tumors. The radiation therapy developed slowly due to a lack of understanding of radiation effects. Becquerel's discovery opened the door. Furthermore, radioactive materials found their way into various industrial applications, including radiography and gauging. The contemporary reception of Becquerel's discovery was initially met with a degree of skepticism. Some scientists questioned his experimental methods or doubted the authenticity of his findings. However, the independent confirmation of his results by subsequent researchers, particularly the Curries, quickly dispelled any lingering doubts. Becquerel's meticulous attention to detail, his careful documentation of experimental procedures, and his honest appraisal of limitations of his research all contributed to the eventual acceptance of his findings. Subsequent revisions and deeper understandings of radioactivity revealed the complex nature of the phenomenon. It became evident that radioactivity involved the disintegration of atomic nuclei, leading to the emission of alpha, beta, and gamma radiation. Rutherford and Frederick Soddy formulated transmutation theory, which proposed that radioactive decay involved the transformation of one element into another. This theory, initially met with resistance, eventually revolutionized our understanding of nuclear physics and laid the foundation for nuclear chemistry. Further advances included development of quantum mechanics, which provided a theoretical framework for understanding the processes governing radioactive. The direct influence of Becquerel's work on others extends far beyond those immediately involved in radioactivity research. His meticulous experimental technique and his willingness to challenge prevailing assumptions served as an inspiration to generations of scientists. His work demonstrates power of careful observation and importance of remaining open to unexpected findings. His discovery of radioactivity stands as a testament to the transformative potential of serendipitous events carefully analyze. Becquerel's discovery also fostered the development of new instruments and techniques for measuring radioactivity. Geiger counters, scintillation detectors and cloud chambers were all developed to detect and quantify radioactive emissions. These instruments not only advanced understanding of radioactivity but also found wider applications in various fields including medicine, environmental science and archaeology. Later, nuclear magnetic resonance imaging, or NMRI, emerged from nuclear physics. It allowed physicians to non-invasively observe the internal workings of the human body, revolutionizing diagnostic medicine. Further refinements of these techniques, as in positron emission tomography, or PET, enabled scientists to probe the brain's activity in real time. All these advancements share a common intellectual ancestor in Becquerel's initial observation. Critiques and revisions of Becquerel's work, while relatively few in number, have largely centered on his initial interpretation of the phenomenon. Becquerel initially attributed radiation to a process analogous to phosphorescence. While his initial hypothesis proved incorrect, his willingness to explore this analogy and to challenge prevailing assumptions ultimately led him to his groundbreaking discovery. Furthermore, his focus on uranium rather than other phosphorescent materials, was fortunate. Uranium's radioactivity is comparatively strong, yielding clear measurements. Were his focus elsewhere, his results might have become obscure. In conclusion, Henri Becquerel's 1896 paper occupies a seminal position in the history of science. His discovery of radioactivity revolutionized our understanding of matter, energy, and the structure of the atom. His meticulous experimental work, his careful observations, and his willingness to challenge prevailing assumptions laid the foundation for further investigations. His discovery spurred the development of new scientific fields and led to numerous technological advancements. From diagnostics to energy production, Becquerel's discovery continues to impact modern life. Becquerel's 1896 publication represents a moment of profound insight, a testament to the power of scientific curiosity and dedication. Though Becquerel may not have initially recognized the full implications of his findings, posterity has recognized them as among the most momentous in physics. The story of Becquerel's discovery serves as a reminder that even the most unexpected observations, when pursued with diligence and rigor, can lead to transformative breakthroughs.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.